Hello, everybody. My name is Zane. I'm a material science master here at UNF. Trying to get my degree. I'm working on something cool called Paleodetectors. You guys are going to learn a lot about that here in just a minute. There's a lot of context that's involved in these, some really cool stuff that we're going to be talking about. And it's October, and it's a little on theme for Halloween, some parts of this. We're going to see those later. So let's go ahead and get this started off. So when we're thinking about the night sky, you look up, you see a smattering of stars and other bright cosmological objects. Tonight, though, we're going to be talking about what we don't see. And we're going to find out that our universe has a lot more than meets the eye, about 6 times as much, actually. And to start that off, we're going to go back in time to the 1930s to talk about a man named Fritz Zwicky. Fritz Zwicky, he was investigating the motion of a cluster of galaxies, and he noticed that a bunch of the individual galaxies inside that cluster were moving at incredible speeds. So fast, in fact, that they were actually moving faster than the escape velocity of that cluster. And it should look a little like this, where some of the galaxies go in, they fly away, but they don't. And he noticed this, and he thought that was very strange. And he actually said, there must be some kind of unseen, invisible matter, some kind of mass that is giving it the gravity to hold it all together like some grand cosmic glue. But he was a little bit of an eccentric, and people didn't really take him seriously. So it wasn't until about 30 years later, when a lady by the name of Dr. Vera Rubin was measuring the velocity of stars within a galaxy, and she noticed that the stars along the outer rim were traveling at relatively the same speed as stars closer to the center. Now that's strange. So the problem with that is that the mass of a galaxy is determined by the star density, and that gets more and more sparse the further from the galactic center you are. So the less gravity, the slower you should be moving according to the math. So this inexplicable phenomena couldn't be helped, but they were like, there must be some kind of unseen matter. That pattern comes back again. And that's influencing the amount of speed that these stars have at the outer edges of these galaxies. So they proposed the idea of a dark matter halo. This kind of conglomerates dark matter around bodies of normal matter, like you and I, but bigger. So using this, they started thinking, all right, what do we know about this invisible stuff that's in our way that we're seeing in all these things, so we can try and isolate it and characterize it and figure out exactly what that stuff is. So we've taken out some notes of what we do know. First thing, we know it's dark. And by dark, I mean it doesn't interact with the electromagnetic spectrum. And by that, I just mean it doesn't touch light. It doesn't mess with it. It doesn't like it. And it doesn't bother with electricity or magnetism in any way. We also know that it interacts through gravity. We see that. That's one of the best ways we've noticed it so far, is the way that it affects gravitational bodies. We also know that it interacts with itself very weakly. And by say we know it interacts with itself, we think it interacts with itself very weakly. We've seen some evidence of that. We can talk about that in the questions if you guys have more questions about that. It's cold, and I don't mean cold as in chilly. And I see that it says slow there. It doesn't mean that it's actually moving slow. It just means that it's not moving close to the speed of light. It's moving relatively slow compared to light, which is what we call cold. It's also stable. The universe has been around for about 13.8 billion years, and this stuff's been around since then, and there's still a whole lot of it around. So it has to be at least pretty stable. So looking at the standard model, and we're trying to allocate these things all onto one of these particles, and none of them fit. But one comes really close. The neutrino is the ghost particle. Did you guys see that? That was scary. The neutrino is a neutral body, so it does not interact with most of the electromagnetic spectrum. So it's what we can call dark. It is also has a little bit of mass, so it interacts through gravity. Its self-interaction is relatively weak. We don't know much about that. Ghosty. It is very stable. We've never seen it decay. Looking for it still. But it is not cold. It is very, very light and therefore very, very fast. It is what we call hot, therefore moving very close to the speed of light. So it's not neutrinos, and so it doesn't really fit into our standard model. So they started thinking, let's make our own version. Let's make a new particle that we can kind of propose to the standard model and see if we can prove that. And using all of these factors, the fact that it's got to be dark, interact through gravity, very weak interactions with itself, cold and stable, and they developed what we call the WIMP model. WIMP model's nice. And it comes up with all those things that we just said. Boom. So the WIMP model offers some very natural resolutions to certain quandaries. Gravitational lensing, you can ask about that in the question section. I didn't cover that here. The rotational curves of galaxies, like I mentioned before, as well as the interaction rates of itself and its annihilations. Another thing that needs to be talked about here is that with this proposal, these things should be detectable by a couple of methods. There's both direct and indirect detection. Direct detection is when it comes in and it interacts with matter, it smacks into the nucleus of an atom. It doesn't like to do this very often. This is a very rare occurrence where these little particles are flying through freely, but they sometimes just line up exactly perfectly to transfer their energy into the nucleus of an atom, causing that nucleus to recoil, as you can see there. Another way that we could see these is through indirect detection, where things such as these neutrinos, formed by the decay or annihilation of dark matter, as it breaks apart, it releases a couple things, one of those being some rays and some being some neutrinos. And those neutrinos can interact with other things to cause other kinds of light. And we can try and find those neutrinos. So knowing this, there are some really large-scale labs that are trying to take advantage of these methods of detection to try and pick up these signals and try and really nail down what we're seeing in the galaxy and try and figure all these things out. One of those such labs that is trying to do the direct detection method are the Lux labs. Inside the Lux labs, they have a really giant tank. Let me give you some more context because this place is pretty cool. So deep beneath the ground in South Dakota, about a mile underground, there's the Sanford Underground Research Facility. And this is the Lux Zeppelin experiment. It is about a 5-foot tall tube, and it is just filled with 10 tons of liquid xenon. Really, really big, a whole lot of xenon. Now, it's so deep underground that it prevents interference from almost any of the other pesky particles that could be breaking their way into this facility and interacting. So they're trying to prevent as many of those as possible by going as deep as they can. There's still some that get through, right? There's those neutrinos that can still pass through all the way through and sometimes interact. So they sometimes see those. But there's some other checks that they have against those. So what happens inside this chamber is the chamber is lined with some highly sensitive sensors that basically detect the amount of scintillation. So xenon itself is what we call a scintillator. So when it interacts and its nucleus is moved, its nucleus center is positive and its electron cloud is negative, and there's a slight charge disparity when that nucleus recoils. That charge disparity causes it to emit a slight amount of light. That amount of light is then picked up by the detector here. So, and they have to make this as large as possible to increase the amount of chance that these things happen. These occurrences are super duper rare, right? As we were saying. So they want this to be really huge. 10 tons, not big enough. They want it to be hundreds of tons. They want it to be way more, but it's just not feasible. It's not practical monetarily. So another lab that we can talk about is one in the Antarctica. This is called the Ice Cube Lab. Very cool, one of my favorites. It is humongous. As you can see, they just kind of drilled down through the ice, through the water, and made these giant tubes. Over here in the corner, you can see that is the Eiffel Tower. That is just to give you guys a scale reference to how large this facility is. So now these tubes of light, they are set up to detect what we call Cherenkov radiation, which is when certain particles go in. Yeah, so it is a radiation that is emitted from secondary particles after a neutrino, including those created from dark matter annihilations, occurs. So whenever they happen and pass through, those neutrinos are then emit this light as they pass through these tubes, which is then detected by them, and they're like, all right, this is a neutrino of this much energy. Was that the dark matter one? No, that wasn't it. They haven't found it yet. They're still looking for that one. There's a lot though, so really cool stuff. Both these labs have one thing in common, and that is scale. They're making really, really big labs because they are doing what we call live detection. Live detection begins as soon as you push the start button. You build the device, now you're recording, and now you're going forward. And they've been up for about 20-ish years. And they have a lot, they're really big, so they should be picking up a lot of stuff. This is the exposure equation. So this is what they're trying to optimize. They're trying to get as much exposure as they can. You guys can just ignore this for right now. This is just about the energy of the particles, how they fluctuate. But for right now, we're going to be talking about the area and time. So both these guys are just trying to scale as much area as they can to compensate for their lack in time. 20 years is not very long in the cosmic scale. Conversely, I'm trying to propose, well, not me, other people have done this, has been worked on for a little bit, but this is the project I'm working on, an alternative method. We're going to turn this on its head. Instead of maximizing our area and going for a little time, we're going to be looking way back in time at things that have been exposed for up to billions of years since the beginning of Earth. And they're very, very small, but that scale is great. So for instance, if this thing is 10,000 times bigger than our rocks, the xenon, let's call that, it's called the xenon, right? The 10 tons of xenon is about 10,000 times bigger than our rocks, but we have a billion times more time. So we end up with a lot more exposure in the end. So paleodetectors have time scales of up to a gigayear, as I was saying, a gigayear just being a billion years. And they have they're really good. So these ancient rocks sitting deep in the earth are just exposed to this radiation at all times. And every once in a while, for these past billion years, they have these tiny little interactions where these dark matter particles hit those nuclei. And sometimes it'll extend it enough that it'll leave a tiny little scar in that rock. And that tiny little scar will stay there until we dig it up, cut it open, and look at it. But it's really, really small. So small that for the longest time, we couldn't see it. And so people didn't really care. But recently, technology has been developing and evolving. It's so much so that we're able to now what we call etch and make those small little scars bigger. So what's going to happen here is we are going to take these rocks, once we've dug them out of the ground, and we're going to chop them open, and we either bathe it in some acid or some plasma or something like that. There's kinetic and chemical etching. And either way, what's going to happen is the surface is going to be eroded, but the surface is not eroded evenly. The parts that are already damaged by these cosmic particles and other interactions are going to break down faster. And since they break down faster in such a way, they actually maintain their shape and other characteristics. So because of that, we make them big enough that the size is now slightly larger than the amount of light, the wavelength of light that's needed to actually get in there. So now we can actually see these scars optically. Big deal. That's really cool. So, sorry. Looking at these things are on the nanometer scale, right? Nanometer, for example, is very small compared to a centimeter. If you compare a nanometer to a centimeter, that's like comparing a soccer ball to the size of the Earth. So making those good things go from nanometers up to micrometers is nice. So we can actually see those things once we do that. Now, the problem is these things are deep underground for a very long time. There's a lot of things you have to consider. You can't just grab any old rock out from the ground. It's going to have too much noise. There's a whole lot of other particles that are also causing these similar tracks. So in order to do anything about that, we have to pick very specific things. And in order to pick specific things, you have to know what problems you're looking for. So things that we have to watch out for are cosmogenic sources. These are things that are coming from space. Cosmic rays from supernovas exploding so far away. Neutrinos, muons, other things happening in our atmosphere, breaking down, coming in and hitting these particles. Now we can prevent that by dig deeper. You know, we get these things from lower in the ground, we're going to be able to ignore most of the stuff that comes from space. There's also the radiogenic backgrounds. Those are things that are occurring from radioactive decay. So Earth is full of radioactive substances. Specifically in the crust of the Earth, there's a lot of uranium-238. And that breaks down and leaves alpha particles, thorium, and all kinds of other things. And it continues to decay, and those things can all hit on these rocks and leave those tracks. So we got to make sure that wherever we're grabbing something, that it's at least fairly radio pure, where it's free of these elements, and the areas surrounding it are also at least low in density of these elements. Furthermore, Neutrons from breaking down of muons in our atmosphere and other things like that. Fast-moving neutrons are very neutral, so they can also penetrate very deep. But those can be blocked by picking things from hydrogen-rich sources. Either the actual sample you want to be hydrogen-rich, or you want its surrounding area that it's formed in to be hydrogen-rich. Hydrogen itself is about the same size as a neutron, so it acts as a little shield and blocks those things from coming in. Neutrinos are pesky. Those are the ghosts. They interact about as much as the dark matter does, and they are causing a little bit of trouble because they're about the same size and energy, but there are some distinct ways we can tell them apart. With those things in mind, we have decided to work on halite. Emily, my predecessor, did her whole thesis on proving the efficacy of halite as a paleodetector. She found some really cool things. She proved that it's able to retain tracks. She proved that it's easily atchable to an exact rate that I showed earlier. And one of the other cool things about it is it has a cubic structure. So cleaving it almost always guarantees that one of the surfaces is going to be flat. And that's very important when you're trying to scan large areas of these surfaces. Because if it's not flat, then you have to worry about the angle, cut it again, all kinds of things like that. So that's one of the reasons we like the halite. It's also found in hydrogen-rich environments as it forms as a mineral evaporate. So it's evaporating from the water sources and collecting in these areas where there's a lot of hydrogen. It's very radio pure, far from the Earth's crust. And it's good stuff. You can mine it very deep too. So it's able to block a lot of these backgrounds. It's nice stuff. Good rock. Halite, by the way, is also known as sodium chloride and more commonly known as salt. It is just salt rocks. This is yeah. I've not etched it via taste yet, but we're working on that. So we do a bit to process these. They're pretty fun. So, oh yeah, I should also mention this. This is pretty important. Another reason we chose this is our local geologist, Barry Albright, had some on hand. So this is the general way that we process our halite for analysis. We take our halite bulk chunks, we cleave it with our rock hammer, smack. And after we do that, since it has a tendency, I told you before, due to its cubic nature, to break along flat paths, we just need to give it one good little tap, and it'll crack into nice little planes that we can use. Then we put it in the plasma bath, Dynapico plasma cleaner, where it is bathed in an argon plasma that is ionized and charged. So these particles are bombarding the surface at an even distribution in order to make those pits that we talked about before. Then we're going to scan the observed surface. We have a couple of tools that we use to scan these surfaces, depending on which kind of samples we're looking at. For halite, we can use either the LCM, the laser confocal microscope. I've got an image of it there. Or we can also use the AFM, which is atomic force microscopy. It depends on what we're specifically looking for. We do use both, though. And after that, we run it through some code and what we call track detection code. This is what Emily also spent a lot of her thesis working on. So after these things are ran through those devices, we get an output of the actual surface profile, and we're able to run that through this code, and it scans and it looks for those tiny little hiccups, tiny little edges, and it marks them based on their shape, which can give us details about their inertia. It marks them about their length, it gives us details about their energy, and we're able to trace those back to the particles that actually started them. Very, very innovative stuff, very cool. And so while we were scanning through these and looking at tons and tons of samples, like 20 rocks, we found a very interesting phenomena, what we call a halo. Once again, there's like multiple halos in this presentation, which I think is interesting. This one means something very different, though. This one is referring to what's called a radioactive halo. So what we suppose this feature is, this is just a very, very small image. This is about 30 microns as a scale bar, by the way. So very, very tiny. But what happened here is a small little pocket of this halite, as it was forming, gathered a small little bit of fluid. And inside that fluid, we suppose that there was some radioactive dust, maybe some uranium, maybe some thorium, maybe some polonium. We're not really sure. Leaning towards uranium because of some other math that we're not going to get into. But basically what happened is over time that sat in there and it decayed. And it decayed and it decayed and started firing off all these decay rates. And as it did, it left at the very end of the trails of the alpha particles these tiny little pores. And so these pores are not just a circle. And since this is radiating outwards, this is actually a sphere of influence. we were to cut this next layer off, we'd see a slightly smaller circle, and cut that next layer, a slightly smaller circle, all the way down to all the way down. And now this is really interesting. This has not been seen before in this manner. Alpha particles do not normally leave tracks in materials like this. This material is too heavy to receive impact from these alpha particles, and yet we're still seeing it. So that's why I'm investigating these. One of the things I'm working on is I'm writing some code that is able to scan the surfaces similar to the other detection code, but this time it's convoluting over specifically ring-like shapes and looking for these among any of the possible radii of those spheres. So if we can find some more of these, there's a lot more we can learn about them. And so that's pretty much it.